in section 12.9, it's page 87. It says find the rectangular box with a volume of 16 cubic feet that has minimum surface area. So the thing with using Lagrangian multipliers is you have to identify two things. Right? You have to identify the constraint function. You have to identify the function you're actually working with. Yeah, so for volume you have x, y, z equals 16. So your points, all your points, x, comma, y, comma, z, comma, x, comma, y, comma, z have to live on this, right? Because that's what a bowl has to have. So that's like, what would that be? Which function is this? Yeah, good. This is my constraint function. This is my, what we call g of x, y, z here. So that's my g. What's the other function that I'm working with then? Of course, what would the surface area be for some rectangular solid? Actually, let's give it better. No matter what you call what, definitely call Z the height. So how many xz's? How many xz's do you have? I have, this is xz here, and this is xz in the back. Right, so I have two xz's. I have two yz's, right? Two yz's. And then I have the top and the bottom. It'll tell me it's open right now. So we assume it's closed. So I got the top and the bottom, x, y. Plus 2xy. So this is my g, that's going to be my f. Tell you honestly, it would work even if it's switched. It's just a multiple relationship. Right? Gradients of each have to be multiple multipliers of each other. So who cares if it's multiple 2 or multiple 1/2? Okay, understand that? So how do I set up my equations? How many equations will I get? 4. So what's the first one here? It'd be fx equals lambda gx. The gradient of one has to equal lambda multiple of the other. So when you take each component of the gradient, set them equal to each other with the multiplier. So what is fx? 2z equals 2y equals lambda gx yz. Okay. And then fy equals lambda gy. Fy is good, 2z plus 2x. And gy is xz. Like here, this will be xy over there. What's fz? Yeah. Fz is going to be 2x plus 2y. And the final equation that you have to play with is setting one equal. Yeah, exactly. So my g of x, y, z, to be a little more precise, and most of the time this doesn't really matter, it's that. I have to subtract the 16 over, set it equal to 0, so that I pretend that it's higher dimension than it really is. When in reality, it's only true for when g equals 0. It only exists in that. In this case, it would be a surface. But, we're pretending like it's a 4-dimensional object, but we're only looking at it 3 dimensions, thank God. So that's that last one is always going to be x, y, z. It's going to be that g function equal to 0. this is not going to factor nice because neither of these have both of these in it. You can't really solve for z or x really nicely in a factored form. So this is where I might start attacking it with just solving for lambda and seeing what relationships I can get. Right? So if I solve, so I got 1, 2, 3, 4. So if I solve 1 for lambda, what do I get? I just get 2z plus 2y over yz. If I solve 2 for lambda, I get 2z plus 2x over xz. Solve 3, I'll get 2y plus 2x over xy. Now, for a lot of this stuff, you have to have, it's not a love for it, a healthy tolerance for playing with equations like this stuff. Because a lot of times, like you're saying, you're not sure exactly what the hell to do. So you could waste an entire couple sheets of paper on dead ends. Oh well. It's all part of the process. You got to investigate, see what kind of comes out of this thing. So see if this leads me anywhere. Since these are all equal to lambda, I can take any two and set them equal to each other and see what I get. If I get anything that looks remotely useful. So if I set 1 and 2 together equal to each other, 2z plus 2y over yz equals 2z plus 2x over xz. One thing I noticed right off the bat, what cancels immediately?
The twos.
Well, the 2's cancel, good. And the z's cancel too, right? So the 2's are gone, the z's are gone. So I end up with z plus y over y equals z plus x over x. That looks promising. Because if you break it down, y over y and x over x, those are going to cancel. Those are both 1, right? So you end up with z over y equals z over x. You guys with me on this? Z over y plus y over y is plus 1. Z over x plus x over x is plus 1. Kill the 1's.
So 1.
Yeah, the z's die, and you bring up the y and the x, and you go y equals x. Does that look useful? Shit, yeah. Right? Now, the problem is, this guy's got 3 variables. So far, I've got a way of replacing, like, y, I can put an x in there. So what do you think I can do to try to figure out, I want to put z in x in place of z, so I have 1 variable in there that I can solve for. Do the same thing we did just now with 2 other ones. And see what you get. Right? Is that a plan of attack? So, which one do you think might be useful for us?
1 and 3.
Yeah, why 1 and 3?
We've got a relation between z and x.
I love it.
So
Notice 1 and 2. Do you see the similarities there? They both have z's in them. And eventually the z went away, so I got a relationship between y and x. Now what do I want a relationship? I want a relationship between z and x, for example. It almost doesn't matter, to tell you honestly, but just the way I said it. I want z and x. So if I do 1 and 3, the y's will die eventually. And in fact, you've already done the work, really, if you think about it. Variables, they're all just stupid letters. If I do all the same work with 1 and 3, what am I going to end up with? Does anybody want to hazard a guess? Whoa. That's not useful. Yeah, I'm going to end up with x equals z, right? Just because of symmetry, just because of the stupid letters. It's going to come out the same way at the end. So now I know x equals y, x equals z. So yeah, now I can plug those in, and I get x cubed equals 16. So x ends up being the cube root of 16. And think back, what shape, if Farmer Joe wanted to fence off his garden, what shape always maximized the area, whatever?
Circle.
Well, circle, yes, but let's say he wants to, he can only think in terms of rectangles.
Square.
So it's gonna be a square, right? So what kind of rectangular solid do you think is gonna actually do this for me, minimize the surface area? A cube. And that's really what's happening here, isn't it? All the sides are the same length is what we're getting. So I kind of, from the very beginning, I should have kind of known where this is gonna head. So this makes me feel good. Right? In a strange way, it makes me feel good, because I'm like, well, that's exactly what I expected to have happen. There's no stupid river in this. Remember the river they always do in? There's a river where they won't go. Yeah, stupid river. All right.
No, think away from us.
I like what you're saying, though. I mean, when I talk to my students about those problems where you have to box off the garden, all this kind of weird crap, I say, a circle, especially my pre-calc students, I actually have them prove that for a given amount of material, a circular based object will always have more area and thence more volume. Did I just say thence? Instead of a rectangular base, right? And that's of course why you see when you have grains and stuff like that, what shape do they use to store them in? Silos, right? With a circular base. So for the same amount of material, you get more volume. Save money over time. Good, right? Okay, is that cool? That's gotta be cool because you're done, basically, so. If that's not cool, I don't know what else to do. Any other questions from
Number 28.
28 in the same section?
Yeah.
Let's see. This one says, given this, okay. And real quick, a little thing about this here. How would you, when you get here, you do have to take a second and verify that this does what it's supposed to do. I mean, currently, I just know it's either a max or a min. So then you should throw it in and show that whatever other point you pick, this is going to be bigger than that. Right? So the minute you find one other point that's more than this when you put it into the surface area formula, that's the proof. You've just shown that that's the smallest. Because either it's the smallest or it's the biggest. If I see another point that makes it bigger, then that must be the freaking smallest, right? So that's a quick way to kind of prove, in this case, that it is what it's supposed to be, minimum or maximum. So here, it's the same idea. They got this big old U up here. They gave me the F, which is nice because my constraint function is the second guy, right? There are G's inside of that one. That kind of sucks, but oh well. So we'll just call it something else. We'll call it, this is my constraint M. So, again, what's got to happen here?
It's also finding partial derivative.
Exactly. I mean, once you get the process down, all it can do is throw uglier and uglier functions at you. Right? So like in algebra, you get a process down, then what do? They throw some decimals at you. Right? So here the process is pretty straightforward. You find your partials, you set it equal to multiplier of the other partial.
So
Cool.
you do the exact same thing over here.
Oh yeah.
Except you're just gonna deal with
They just call it a utility function now because it's some economic thing that personally I don't like economics, but if that jazzes you, you can look up what the hell utility function means and see what this does for you. But mathematically, what do? This will be ux equals lambda mx, right? Or not ux, sorry, ul. My variables are not L and G. And then UG equals lambda mg. And then finally, 4L plus 2G equals 12. Let me be really specific over here. That's my M, right? To officially get your, in general, what the G function is, you have to set it equal to 0, pull all this stuff over it, and pretend like it's not equal to 0. I really hope that a few of you guys understand that. If you don't, you can still do the nuts and bolts. It still works. So I'm not going to do this one all the way out. How do you, what's UL?
64 thirds.
Good, 64 thirds.
L to the negative
L negative 1/3, G to the 1/3 equals lambda times what's ML? 4. All right. That looks promising. Now, the weirder they make their functions that you have to use, the weirder the system of equations might get to make sense of, to know which way to go with it. UG, let's just get this to the point and see if you guys can see which way to go with it. UG would be 32 over 3, L 2/3, G to the negative 2/3 is lambda times 2. Doing anything respect to G that time. And then finally, you get this guy. So there's 1, 2, 3. Yeah, so what could you do there?
solve for lambda of those equations and set the solution.
Do that. And they look really nice. They look like some of them want to complete each other, right? Because some of them have negative 2/3 and some of them have negative 1/3 or 1/3 and 2/3. So it looks like they want to complete each other. All right, cool. So I'll let you guys finish that out because that's not that bad from there on. Okay. But trust me, if you go any deeper into physics, these Lagrange multipliers will come back and you will love them. I don't know if you are okay with them now. You should be okay with them. They're actually, the math of them is not as nearly as bad as some of the other stuff we've done.
Jeff,
Yeah.
so on the test, would you mind if to use Lagrange multipliers or the method you taught us before Lagrange multipliers?
I'll try to be specific. In fact, if I don't say use Lagrange multipliers, I mean don't. Like on the practice test, I have one problem that says use Lagrange multipliers to do this. Yeah. So if I don't say that, don't do it.
Oh.
Cool. Any other questions from homework stuff? Okay, so a little review from last time. I want to look at the quick quiz from 13.2. And then we're going to try to do 13.3 and 13.4. We'll see what happens. So first off, let's just do the main two types of problems we really have in this section. Really the main two types of problems are, can you do double integration if it's given to you? And can you switch the limits if you need to? Or set them up, right? So can you play with the limits? Can you do the integration once you get it set up? So let's look at this one. 30 says yeah, 13.2. Now take a second and first sketch the region that I'm integrating over. Here?
Yes.
Sure.
Is this 13.2?
52, yeah. We did one a lot like this the other day when we switched the limits of integration. Personally, I kind of like to take a second and make sure that my eyes are looking at the right thing, because when you're trying to match the integral symbol with the dx, dy, dz, and soon we're going to have dz, we're going to have triple integration. It's going to be which goes with which variable does what. Holy crap. So y goes from 0 to 2, x goes from 0 to 4 minus y squared. So the nice thing is right there, y goes from 0 to 2, so I can only go up here. I can't have anything down there. Right? So while y does that, x goes from 0 to this thing here. So the way to think about it is, while y goes from 0 to 2, x is starting from 0 and going to this. So x is going from y equal to 0. Oops. It's going from x equal to 0 to this. So where is it going from to exactly? Well, what's the shape that I've got here? Let's start off there.
Parabola four, so it's 4 units to the right.
It's good, and it's going down, and it's going to be,
It's going left or right? Should left.
so it's definitely got there, right?
Oh, no,
When y is 2, x is 0.
It should be on the x-axis, right?
Why?
The
Well,
parabola.
sure, it'll work.
It's an upside down
So what do I have here? So if I've got x equals 4 minus y squared,
It's half of
y squared equals 4 minus
Going
x.
left or right? It's one of those.
Because it's negative one.
Hopefully left, right?
it's half of
So it's gonna come down, out.
So if y is 2 or negative 2, what would your x output be for that?
0.
Now, of course, y can only go from 0 to 2, though, right? And normally a parabola that opens sideways opens this way. This is negative, so it's going to open that way.
That's right.
Cool, okay. So at 2 it's that, at 0 it's, yeah, so when y is 0, x is 4. So it seems to be just this piece here, because it's not allowed to go down there, because you can only have y values from 0 to 2. Okay, cool. So as my y values go from 0 to 2, my x values go from 0 to this. You guys see that? Is that cool? So another way to look at this is, how do I pick up all the points that I can use in a very systematic manner? Well, I let y go from 0 to 2, and as I do that, I let x go from 0 to that curve out there. So at 0, for y equal to 0, I'm going to pick up all these points. It goes from 0 to that curve. At y equal to 1, it's going to pick up everything from 0 to that curve. And of course, everything in between. So I end up getting all the points I'm allowed to use in between. So when I say that, and I'm hoping you guys have done enough stuff back in Calc 2, we did semi-similar stuff to this when you had to rotate stuff and you had to worry about the limits and what it was going from to. when it goes from this to this, that's from the y-axis to that curve, right? That's what it's doing, going from there to the curve. What are we doing? So if I wanted to turn this around, which I really wasn't going to talk about now, but we might as well, we get a nice picture there. If I wanted to turn these limits around, how could I do that? If I wanted to instead go dy dx. So as x goes from 0 to 4, what does y do? It goes from
0 to 4 or square root of.
I like it. And of course, when you do this, you get plus or minus, but we know we want the positive side, right? We want the upper part of that parabola. What are we doing there? Is that cool? I mean, once you get the region drawn out, it's not that bad to turn those limits around. As long as you can look at it the way, you know, the outer one is going to be just the pure numbers. So as x goes from 0 to 4, what does y do? It goes from 0 to this function. And what's that function if I rewrite it? If I rewrite it in terms of x, square root of 4 minus x. Because I don't want the bottom part of that parabola. Okay. All right. So go ahead and now this should be the easy part now. Just attacking something with integration normally is the nice part. Because you know how to integrate most things. So go ahead and try to integrate that thing. See what you get. When you integrate this inner thing, what do you get? It's with respect to x on the inside there, so what do you get? Cool. And that's kind of an easy thing to forget, that poor little y dude, and give him an x, right? A little easy to forget that. So now you gotta plug in some ugliness, but oh well. We get 4 minus y squared over 2 plus 4y minus y cubed. Is that cool? Everybody see what happened there? Just plug those limits in for x. And that's another little thing in the middle there. You've got to really keep track of which letter you're talking about at that moment. What am I plugging this stuff into? Now, to integrate that, I might want to clean that up a little bit, right? So I'll get 16, so divided by 2 is 8, minus 8, so that's minus 4y squared, right? Plus y4 over 2. And of course, there's not a damn like term in there, but now you just integrate that. with respect to y, you get, what do you get, 8y minus 4/3 y cubed, plus y5 over 10, plus 2y squared, minus y4 over 4 from 0 to 2. Let me see you say it. You know, actually doing the integration is the really nice part. Having to set up or play with the limits, that's the sometimes difficult part. For the rectangles, it's easy as hell. You just switch them. Who cares? But when they're going between functions, that's where you have to be careful. And then, I don't care about that. You just plug 2 in and see what the hell comes out, right? So we got something.
I got 376 over
376 over
theory. Over theory.
30?
Zero, yeah.
And then, I like it. So just reduce that or make it a decimal, whatever you feel like doing. Alright, cool. How are we feeling about that type of thing so far? So this is what, I think a lot of you guys came in expecting this sooner, but it's just the way that it's kind of set up. We needed to first talk about taking derivatives of multivariable things before we talk about taking antiderivatives of multivariable things. Right? Okay. So let's look at that quick quiz then, at 13.2. Oh, here. I do have a few more extra copies if you need it. Want? Anybody else not get a copy of the practice test? So go ahead and try out this 13.2 quick quiz. Try those out. Let me know if you have some trouble. We did, but we didn't do it. You want it back? Another cup? Got it?